So we are about to talk about tree nutrition and fertilization here in just a few minutes. I just wanted to remind everybody that this is supposed to be and is designed to be a refresher course that you take right before you would take the exam. And so I hope you have read your chapters, um, especially chapters that you are not familiar with from having worked in the field. I also encourage people to go out and find a mentor, someone that can help you to understand this material. I know some people work in offices, some people might work in plant healthcare, some people might work in the production end of pruning and things like that, and aren't familiar with all the areas of the exam. So find yourself a mentor, somebody you can share experiences with that are in areas where you feel the weakest. All right, so let's go ahead and get started. We're going to be talking about what elements are actually required by the tree. We're going to talk about fertilization objectives. In other words, why do we want to fertilize? Is it necessary? How much do we need? That type of thing. Types of fertilizers that are out there. There are different formulations. What makes them different? We'll talk about methods of fertilizer applications. What happens if you fertilize too much? And we'll also speak about determining the actual nutritional requirements and availability. There are 17 of these essential elements that trees need to grow and develop to reach their genetic potential. Most of these elements are usually present in sufficient quantities in a forest setting. So remember, we're studying arboriculture, and arboriculture is the study of trees as individual entities and not as forest ecosystems. So most of our trees are going to be in someone's yard, or they're going to be in some other type of synthetic environment like planters or between sidewalks and curbs. They might be foreign to our areas, so you might be bringing in trees that are a bit out of their comfort zone, things like that. And so that's why we're going to talk about these specific needs, because these aren't necessarily available because we interrupt that natural nutrient cycling that goes on in the forest, the decomposition, reabsorption, and reuse. So these urban trees, they may be grown in soils that do not contain these elements in sufficient amounts, either because the soil's been damaged, or it wasn't the right mix of soils to begin with, or we are interrupting that nutrient cycling. These elements come in two different groups. There are macronutrients and micronutrients. Macro means large, and micro means small. And so macro elements are the ones we're going to need the most abundantly. And these are nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, plus obviously the gases such as carbon, oxygen, and hydrogen. The micronutrients out there, these are ones that are really only needed in very small amounts. The tree needs them for very specific chemical compounds. But without them, the trees would be sick or chlorotic or not be able to defend themselves. These are boron, chlorine, copper, iron, manganese, molybdenum, zinc, and nickel. Again, macronutrients are required by the tree in large quantities. Again, it's because it's macro, right? So large quantities. Nitrogen's also the most limiting, or usually the most limiting micronutrient out there. When we say a limiting macronutrient, think of buying a box of cake mix, and on the back, it says it requires 3 eggs and so much oil and so much water. If you only had 2 eggs, you wouldn't be able to make the whole box, even though if you had everything else there, your limiting factor are the number of eggs available. So nitrogen is that. If you think about nitrogen in its pure form, it's a gas. And so it wants to liberate itself to the atmosphere. Nitrogen is available in decomposing organic matter. So as it's released it's in a matrix of some type that the plant can use and absorb. However, eventually that matrix breaks down from soil microorganisms chewing apart the carbon bonds and things like that, and the nitrogen gas is liberated. So that's why it doesn't persist in the soil for very long, and that's also what makes it the most limiting factor. In urban environments, leaf litter is removed. So if you don't have the decomposition of this organic matter, guess what you're not going to have? You're not going to have sufficient amounts of nitrogen. N, P, and K are required in relatively large amounts. So just some little foreshadowing here, but N, P, and K, you will always see these three elements listed in this order and represented with these letters: nitrogen, phosphorus, and potassium. There are also some secondary macronutrients such as magnesium, calcium, things like that. But again, these are usually available in sufficient quantities. Now, talk about the influence of soil pH a little later. Nitrogen under natural conditions comes largely from the decomposition of OM, or organic matter. Removal of leaf litter and other natural sources of nitrogen can disrupt the cycling of nitrogen in the soil. Much of the nitrogen can be lost due to leaching or to volatilization. Volatilization is when it's liberated to the atmosphere. That's when it becomes a gas. Leaching is when it's in a form that holds together long enough so that it tends to migrate through the soil profile and actually can get below the root system, so it leaches out of the effective area. Nitrogen deficiencies are common in sandy soils, because water is going to perk down through sandy soils much quicker. They tend to be pretty deep. They're also low in organic matter. And if the more you irrigate or the heavier the rainfall is, the more likely it is to wash it or leach it down through that sandy profile. Nitrogen deficiency causes reduced growth, smaller leaves, and chlorosis of the leaves. You will see this term chlorosis used over and over again. There are a number of disorders that trees can have that result in yellowing of the leaves, or chlorosis. So we'll come back and talk about chlorosis a lot before the end here. It's important to recognize that nutrient limitations do not equate to nutrient deficiency. A nutrient deficiency affects the tree's overall health. And if you think about sort of a Gaussian distribution, if you're familiar with Gaussian distributions, which I'm sure you are, you might just not know it was a Gaussian distribution. You have a bell curve, and in this bell curve, we can draw sides down here and say that most plants are okay in between here. So this is to have a nutrient deficiency, nitrogen, the available nitrogen. So if we say that this line is nitrogen available to the plant, so it's just slightly available here. Here's the bottom axis for you, and the other axis for you. So as nitrogen becomes less available, you actually get outside of what the tree can handle. So this might be a half a pound of nitrogen per 1,000 square feet, and this might be 9 pounds of nitrogen per 1,000 square feet over here. So once we drop below that, then you're actually going to have a deficiency that's going to result in poor tree health. Limitation is that if I'm over towards this side of the bell curve right here, then the tree's not going to grow as fast as it would if it were on this side, but it's still going to be a healthy tree. We're just taking our foot off of the accelerator and backed it back here. So now we're going to talk about micronutrients. This is micro, so these are the small ones required in lesser quantities. And in fact, these things can actually become quite toxic at higher levels. Deficiencies of iron, zinc, and magnesium can lead to serious plant health problems. Molybdenum, copper, chlorine, boron, and nickel are less likely to be deficient. These are what make up our basic soils, so it'd be very rare not to have these. We can do it clinically in the laboratory and show that it does cause problems, but out in the real world, you're not very likely to see this. So deficiencies of this iron, magnesium, and zinc can result in, here's our word again, chlorosis. So this chlorosis, again, this is the yellowing of the leaves. So here is a fertilizer, a bag of fertilizer. This fertilizer has some analysis on it. Notice again, we have N, P, and K. Nitrogen is always N, phosphorus is always P, potassium is always K, because I think that's how you spell it in Greek. So when you look at a bag of fertilizer, it'll always have these three numbers. And remember, 0 can be a number, so you might have like 2000, or you might have 050, or you could have 0010. So this is, but you'll always see all three of these represented in P and K. So the fertilizer analysis gives the composition of the fertilizer expressed as a percentage by weight. So there are some questions in your book about this. I would suggest you look at these quite closely and work some of these word problems in a number of different ways, because these will be word problems, and there's some simple math involved that you'll need to know. So what this means is this is 20% of this, the weight of this bag is nitrogen. So total nitrogen, 20%. So if we had a 100-pound bag of fertilizer, that's going to be 20 pounds of nitrogen, 5 pounds of phosphate, and 10 pounds of potash. So notice that that phosphate and potash are actually compounds. They're not just elements by themselves. So it's P2O2 and K2O over here. So these compound potassiums often referred to in its available form as potash, because that's how they derive it, is from ash. And phosphate also it's available in this compound. Instead of phosphorus, it's phosphate. So yeah, so just realize that these two are compounds and this one's an element. Now, if you add all these up, 25 and 10, what do you have? You have 35, right? And I said it was a 100-pound bag. What's all the other stuff in the bag? It could be sand, it could be organic matter, it could be other polymers used to slow the release rate down. There's a number of things that are added to these fertilizers to make them easier to spread. Now, a typical fertilizer bag is going to be 50 pounds. So remember, I made this ultra easy by making it 100-pound, pretending that it's a 100-pound bag to get that 20 pounds of nitrogen. But if it's a 50-pound bag, then that's actually only, since it's 20% of 50, that's only going to be 10 pounds of actual nitrogen. Again, these are always listed in N, P, and K in that order, everywhere in the world. So that's an international standard. So here's another quick just example here. You have a fertilizer analysis. You have a 50-pound bag. So whenever you have something that shows up that's all three numbers, this is referred to as a complete fertilizer, because it does have some components of N, P, and K. So this would mean, since it's a 50-pound bag and we have 10, 10, 10, that's going to contain 5 pounds each of nitrogen, right? Since it's half the amount. So it'd be 5 pounds of each one of these. Again, it's a 50-pound bag, so that's only 15 pounds of product in a 50-pound bag. Seems like I see a question popping up. Is that something we need to take a look at?
Sorry, I was in the chat. If we could convince people to stop raking their leaves and mulching them instead, would chemical fertilization become moot?
It would over time, and it depends on how horrible the soil is and stuff like that. But our best management practice is to mulch under the entire drip line of the tree, which is rarely something homeowners want to look at. So there are good forms of fertilizer out there that can mimic the natural nutrient cycling that are organic and things like that. But I guess the quick answer to your question is yes, if we didn't rake up all the leaves, then we would get closer to having that forest-like condition. But also remember, out in the forest, you have decaying logs, you have multiple types of trees, not just one species. You have multiple species of trees that are all contributing to that soil environment. And in a typical forest, those soils have been working that out for millennia. So once we build a home or scrape it off and plant a tree, it takes a very long time to restore those soils. So hopefully that gets to your question there. So trees seldom need a complete fertilizer. So it wouldn't be normal that you would need a 10-10-10. You might need, like in the Piedmont region of Georgia, we have very high phosphates in the soil. And so typically our center number is going to be 0. So it might be 2104 or something like that. But it's highly variable. We did studies in the city of Atlanta examining soils from the north side down to the south side, and it was not uncommon to find tremendously different soil types. So we'll talk about prescriptive fertilization, but that is sort of a key thing. Apply phosphorus and potassium only as soil tests indicate. You might have noticed, if you're old enough, we used to have lots of phosphorus in our dish soaps and in our laundry detergents and in our hand soaps, and now they're all phosphorus free. And a lot of that is because of the phosphorus runoff that's occurred, where the phosphorus would get into the water systems and you'd have these algae blooms. And so as a result, we took them out of all those products, and now we're trying to limit their use in the environment through commercial applications of fertilizers. So there are lots of different types of fertilizers, like I alluded to a moment ago. Under the organics, we have manures, which are pretty good stuff, but they're not the total answer. And if you go back to tobacco farming back in the 16 and 1700s, the farmers used to try to fertilize with manures, thinking that was the only way they could get it. And once they did it for a couple of seasons, it would ruin the tobacco. It wouldn't have the same taste anymore, and people wouldn't buy it. It created deficiencies in the soils by using just this one source. Not too long ago, we were using sewage sludge on a regular basis. These are the biosolids. So like you go to a water treatment facility where all of our things that we flush down the toilet wind up getting oxygenated. It goes through a microorganism that feeds on it. And then at the very end, there's this leftover sludge, and this sludge is dried out and pelletized. And that does make for a pretty darn good fertilizer. Again, not something you want to use over and over and over again, because there are heavy metals that show up in our sewage sludge. Just think about all the drugs and things like that wind up in our water system from urination or just from flushing them down the toilet. So that stuff is inorganic, so it's not decomposed by those microorganisms very well, and it persists in the water supply and definitely persists in the sewage sludge. Another good organic is bone meal. Bone meal can be decomposed. It's got lots of calcium in it. It's got a little bit of nitrogen in it. It's made up of bone, obviously. So bones have all these essential elements usually. Cottonseed meal. Cottonseed was a big thing, trying to get rid of it back when cotton was mass produced here in this country for textile industry. They didn't know what to do with the seeds, and so they would just start grinding these seeds up. They'd feed them to their animals. They'd put them in their crops. They would even just dump them into rivers. There would be so much of it that would collect all over the Mississippi River. There's also some synthetic organics. So if you recall, the word organic means a carbon compound. There are lots of carbon compounds out there. Gasoline is a carbon compound, so technically gasoline is organic, right? So be careful of how you use the word or think of the word organic. Some examples of synthetic fertilizers or synthetic organics would be like urea formaldehyde, where they take a urea molecule and bind it onto this giant carbon string, which we call a polymer. So it's something that's man-made, but it's on this carbon infrastructure, so that makes it a organic compound. And these are broken down by soil microorganisms. We have inorganic types of fertilizers, granular, things like Miracle Grow, some of the slow release fertilizers. We'll talk about the difference between synthetic organics and slow release fertilizers as being inorganic. We'll talk about that in just a second. Fertilizer rates. So if you think about a rate, that is time over distance. So it's like your miles per hour. I mean distance over time, sorry. Miles per hour is a rate. So fertilizer rates have to do with the application, how much of the product you're putting down over a certain amount of area. So the rate of fertilizer should be applied depends on the age of the tree, the health and species, the form of the fertilizer, the method of application, and the site conditions. All of these are variables. Slow release fertilizers reduce the amount of nutrients that can be leached and also reduces salt and fertilizer burn. We'll talk about fertilizer burn a little later. Fertilize with a slowly soluble source with at least 50% of the nitrogen in the form of water insoluble nitrogen. Whenever you read a bag of fertilizer or you pick up a container of pesticide, you're going to see this alphabet soup of things out there. So, and these are also international standards. So whenever you see WIN, W-I-N, that's water insoluble nitrogen. And it might not show up on the printed label on the product. So you might have to go to the complete labeling of the product, which you might find online. And you're looking for a product that has a salt index less than 50. And this is a standard. This will be something that you'll see show up on your exam pretty much for sure. So here we're talking a little about rates. So here we're going to talk about the amount per area. The general recommendation for slow release fertilizer is 2 to 4 pounds of actual nitrogen per 1,000 square feet of root area. So these are all the background information you need to know to solve these word problems that I alluded to a little earlier. Quick release fertilizer rate should be 1 to 3 pounds of actual nitrogen per 1,000 square feet, not to exceed 4 pounds annually. So whenever you see the word actual, let's see, where was it? Actual nitrogen, so right there. So whenever you see this word actual, that's talking about only the nitrogen. So again, if you have that 100-pound bag of 10, 10, 10, that means you have 10 pounds of actual nitrogen in that 100-pound bag. Hopefully this makes sense. And so you'll have to calculate how much of that bag is needed for 1,000 square feet for it to be 1 pound of nitrogen, of actual nitrogen. So under the slow release, it's 2 to 4 pounds. And the reason it's 2 to 4 pounds is because this stuff persists in the environment a lot longer. So this is delivered over a period of a year, whereas you might have to do a couple of applications per year of the quick release fertilizer. So you might put down 1 pound now and 1 pound in the fall, or 1.5 pounds now and 1.5 pounds 6 months later, or something like that. So that's the difference between a quick release, or that's why the difference between a quick release and a slow release. When do we put these things down? Nitrogen uptake peaks during the spring and summer. Why do you think that is? Because all that organic matter was deposited in the fall, but the microorganisms are sort of dormant because it's cold. So as early spring kicks in, those microorganisms begin to wake up and they begin to munch away on all that organic matter, releasing the nitrogen. So we want to mimic what happens out there in nature as far as good timing goes. The most limiting factor in fertilizer uptake is water availability, because remember, you can have all this nitrogen in the soil, but if you don't have water to dissolve it into, the plant can't take it up. If you recall our discussions about the xylem tissue and what the xylem transports up into the canopy. The soil type determines how often to fertilize. So clay soils have a very high cation exchange capacity, or a CEC, which equates to less frequency of fertilization when compared to something like a sandy soil that has a fairly low CEC. Fertilizer uptake is greatest during active root growth. Active root growth occurs a couple times a year, so we know that we like to plant in the spring. We also like to plant in the fall. We plant in the fall because the microorganisms are working in the fall. The soil temperatures are in that right range to release some of these elements, so the roots are taking advantage of it. They go into dormancy in the winter and they come back out in the spring and go up again. So obviously, whenever roots are growing, that's when uptake is going to occur the best. All the really small, fine hair-like roots out there get fried off during the middle of the summer when it's too hot. So there's not a tremendous amount of uptake during the actual summer months as compared to spring and fall. Apply quick release forms in the spring through the fall. Slow release anytime soil moisture is adequate. So sometimes these slow release formulations can last up to 10 months. And they release, remember, on microbial activity, not just on water alone. So if you put it down in the fall, it's going to work in the fall, then go dormant, and then come back to work again in the spring, and you'll get your 10 or 11 full months of activity out of it. That's why you can do it any time of the year. The quick releases only persist in the soil for a few weeks. So that's why you want to get them down in the spring and the fall. There's a number of application techniques out there. Surface application, which is where you're just putting the granules of the product or you're spraying it down just on the very surface. You might think this would tend to mimic what happens out there in nature, because that's where the leaves fall, is on the surface. Some of the advantages, so you're mimicking that. It's very effective at providing nitrogen to the trees. It requires the least amount of time to perform. You've got a guy out there with pushing, a spreader of some kind. It goes down very quick. You might even have somebody out there just with a bucket, just throwing it out of the bucket by hand. That's not the greatest way to do it, but it is a way to do it. So it does not require sophisticated equipment. It is applied in the location with the greatest amount of uptake. Most trees' active roots, again, are in the top 6 to 12 inches of the soil. These fertilizers tend to be the least expensive types of fertilizer. However, it does have a greater potential for volatilization. Remember, being pushed into a gas, it also has the greatest ability for leaching or migrating off site. So if you get heavy rainfall, it might just wash it down somewhere else. Here's some examples of surface application equipment. You've got the sort of handheld grinder. Here you have a standard type of drop spreader. We like to do subsurface applications, because if you think about what we do a lot is our trees are around turf areas. So if you have a tree that's growing in the turf, you don't want to put down 4 or 5 pounds of nitrogen per 1,000 square feet. In a turf environment, which only likes about 1.5 pounds of nitrogen per 1,000 square feet. So you could wind up burning turf. So one way to get around that is to do some subsurface action. This places the fertilizer below the surface. It's good for trees around these turf areas and places the fertilizer below the grass roots. Maybe, maybe not, but that's what we'll say for the exam. It can be applied, subsurface can be performed in several different ways. We used to use this drill hole method. So we would have this drill bit that's about this big around and then about 18 inches long or so. And you'd have these guys with these big power drills drilling holes out. and then someone going behind him with a bucket pouring these fertilizers into the hole. So we would space these drill holes out every 1 to 3 feet. I mean, yeah, every 3 to 4 feet on this grid pattern. Um, so that was how we did it, and that was not a fun way to do it. Your hands would be numb by the end of the day, and it gives you what we call hot pockets. So it's very similar to driving those fertilizer spikes into the ground where you have this concentrate of fertilizer. So the roots will take advantage of the fertilizer around it, but then when it rains, you have this flush of fertilizer and it can cause root burn. So not the greatest way. These subsurface, I mean, these drill hole methods has an additional advantage, however, of aeration of the soil because you're decompacting the soil a bit. Um, so the spikes, you get the hot pockets like you would here. However, with the spikes, you're going to add to the soil compaction by pounding something into the soil. Exactly where is our treatment area? So here's our crown. This crown has some width to it that we'll call R, and we want 1.5 times the crown radius. So we'll come way out past the drip line. We'll draw this circle all the way around. The closer you get to a tree's trunk, the more sensitive to products it becomes because the root density increases as you get closer to the trunk. So you want to avoid fertilization right up against the actual trunk of the tree. So the fertilization area will look sort of like a donut with the tree centered in the hole there. And keep in mind, you might have trees that are at angles and things like that, so it's not the actual drip line. Try to use this crown radius business because the roots don't care where the sun is. They'll grow in all different directions. The liquid injection method is also a subsurface method. Holes are drilled 4 to 12 inches deep and 12 to 36 inches apart. Fertilizer is dissolved or suspended in the water and can be poured into these holes. Or you can forego the drilling and just use a device that has a soil probe attached to it. The soil probe, you're just pushing it down into the soil, opening a valve and pulling the probe back out, applying several ounces of the product upon every injection. So this has a great advantage because you're getting the fertilizer to diffuse into the soil, so you're creating bigger space and not just these little hot pockets like you would in the drill hole method. And you're also putting it down with water, so it comes with its own carrier it's already dissolved in water. You're putting it right there next to the root system, so hopefully you're going to get pretty good uptake from that. You can also apply fertilizers directly to the leaves. This is sometimes used to correct micronutrient deficiencies. Not all species will respond to this method, but things like that are low in iron can respond, like pin oaks that are turning chlorotic or have chlorosis. You could apply some chelated iron to them, and you get this sort of temporary green up. And again, this is sprayed into the canopy, so you're limited by, if you've got a huge tree, that's going to be very difficult to do. It's going to require very expensive equipment to get it up that high. So it's not the easiest stuff to do, maybe not the best way to deal with chlorosis of that species. So we might think about doing something like micro injections. These are implants, and the injections are inserted directly into the xylem of the tree. So you have this little capsule. I'll just show you what they look like. So these are the capsules. These things are pressurized. You drill little holes. These are filled with fertilizers or insecticides or fungicides. They can be filled with miticides, all kinds of stuff. So whatever you want to deliver to the xylem tissue so that you can translocate it throughout the canopy. You drill these little holes, you put on what's called a pick, and you insert this pick, and then on the back side you have this two-stage container. So it comes like this, and then you squish it together and it looks like this, pressurizing the capsule to about 11 or 12 psi, because trees carry somewhere between 9 and 10 psi internally, so you have to overcome that pressure in order to move the product into the xylem tissue in an efficient way. So that's what the trunk injections would look like. It relies somewhat on transpirational stream to move materials systemically within the xylem. Good for micronutrients, not the greatest use during drought periods. Here in central Texas, we actually had 96 days without any rain at all. And so some of the injections that we did at the very beginning of the season really stressed out some trees. So we had to do some supplemental watering to overcome the problems initiated by doing micro injections, or in this case, macro injections during a drought period. It does require proper technique and frequency to avoid damage, because as you can imagine, every time you drill one of those holes, you are introducing some decay to the main trunk. 11/64 is the common diameter of the drill hole. And so the tree has to react to that damage, has to compartmentalize it. It goes through all four walls of the coated model in order to close up that little hole. So you're going to have some residual scarring, because remember, there is no cellular replacement in plants. So if you give it a couple of years between every injections, the tree gets a little larger in diameter, grows some new clear vascular tissue, and you're able to make another application. Some other additives that you might be able to put into the soil or into the trunks, mostly to the soils here. You can inoculate them with fungal spores to encourage mycorrhizal development. You can put down beneficial bacteria and things like that can help break down organic matter. A lot of our urban soils are so disrupted that regular mycorrhizal and regular types of bacteria that we want, these beneficials, can't grow in those harsher environments. And so we can apply ones that have been specifically selected to be able to survive in these harsh environments. So we can add back soil microbes. We can certainly add organic matter back to the soil, either through surface applications or even in the form of carbon, charcoal. So we can grind charcoal down to very, very, very fine particles, less than 7 microns, and actually flow it like water into the soil for the microbes to eat. We can add vitamins, minerals, seaweeds to these. Seaweeds have a lot of cytokinin in them. Cytokinins help in root development, if you remember back to those hormonal balance things that we talked about earlier. There is limited research and evidence of efficacy on some of the mycorrhizal products. The reason that they say this is because it is a mix. A lot of these mycorrhizal products that you can purchase have soil microbes in them. They have organic matter in them. They have minerals in them. They have seaweed components to them as surfactants. They have yucca in them. So it's this huge cocktail of stuff. If you read the ingredients, the bag has like 60 or to 100 things on it there. Yes, ma'am.
So Dave wants to know, does mulching lawn clippings benefit the tree, or is it used up by the grass?
So lawn clippings are, for a healthy lawn, you want a certain amount of thatch. And so that thatch is incorporated back. It does help the turf. It is something you have to manage. Soil thatch, if you cut too much of the turf every time you're out doing it, you'll accumulate more grass clippings than what can be digested by the soil microorganisms. And so you get this ever increasing thatch layer. If you have not enough of it, you'll see it decrease. So it does help to recycle those lawn clippings. However, it's not going to be the total solution for the whole soil profile that'll help necessarily both trees and turf. Hopefully that answers the question. Again, water, leaching, salt content, and pH may limit the uptake of certain elements. So let's delve into this pH a little more. So we talked about this cation exchange capacity of clay soils versus sandy soils. So the higher it's almost like a magnetic attraction, if you could think about it, as pulling in these cations and how they're going to retain or be released. So this is greatly affected by soil pH. If the soil is too alkaline, Iron may be unavailable to the tree, and if it's too acidic, magnesium may be unavailable to the tree. pH typically has a range. Let's talk about the naturally occurring ranges that you might see in a soil test. You might see something very acidic down here at 4, or you might see something quite basic way down here at 8. So everything above 7 or greater than 7 is basic. Everything less than 7 is acidic. So hopefully you've seen this chart before. You probably saw it in 4th grade. You probably saw it again in high school biology class or something, and you might have seen it in college if you studied any of this there. So, but you might not fully understand it, so we're going to explain it here real quick. So given a certain pH, so at a pH of 6, the width of the element that's represented here, it's copper. So notice copper, the width of this is the availability of that compound or element at a given soil pH. So you can see that the copper line is the widest, the more acidic it gets, and it becomes a little more narrow through the transition here of 5.75 to 6. You can see a big transition here where the copper drops off, but it stabilizes. And then you could look at something like manganese. So the more acidic it gets, the more manganese is available. Notice this one goes down to almost non-existent as it becomes quite basic. So nitrogen has a couple of little anomalies in it where availability will drop off at certain pHs, but nitrogen is pretty much available throughout the spectrum, except somewhere around 4.75, which you might actually find in North Georgia. You would probably never find a 4 unless you are looking at strip mining activity, and you would hardly ever find an 8.5 somewhere. This blue area, this is kind of the Goldilocks zone where everything can be available to the plants. So where I live here in Central Texas, we have 7 to 7.25, so we're somewhere in here. So we do often have manganese and boron deficiencies. Phosphorus becomes a little more bound up than it would over on the East Coast where you guys have more acidic soils. Okay, so salt problems. Fertilizers are in effect a type of salt, but they're just made up of different compounds. They're not like the salt you might think of like table salt, but it does have a similar reaction. Fertilizer burn is the result of an excessive soluble fertilizer in the root zone. So if you get very salt, if the soil gets quite salty, it's going to begin to extract water out of the plant and into the soil, because that's how the water moves, the potential moves across the membrane in osmosis, resulting in the wilting or marginal burning of the foliage or even death. Use of a fertilizer with a salt index below 50 will help to prevent that. Slow release fertilizers are less likely to cause this type of burning. So if you go back in like Roman history, whenever the Romans would come into an area and try to flush people out, they would bring in massive amounts of salt and actually salt the growing fields. And these fields would be unusable for decades, sometimes even centuries, if they really oversalted an area to try to kill crops. So that was an effective way to kill plants. And a lot of our herbicides are actually types of salts. Again, we've talked about leaching a few times. This is the washing of chemicals down through the soil profile. So it migrates down below the root, so it leaches out or leaches into the water table. Soluble nitrogen tends to leach and can be harmful to the environment. If it leaches down into the water table, it can do some not so nice things to us. Only apply it in recommended amounts. Don't overdo it. Again, think back to that bell curve. We want to be in the middle of that bell curve, or maybe even to the low end of that bell curve. We just need to be inside of it to keep the tree healthy. Some people may really want to push some small young trees to grow rapidly, but that's not necessarily the best thing for the tree. avoid overwatering in sandy soils. This is going to help hold stuff in place. We want to fertilize based on a soil analysis. So we want to do some testing. We want to prescribe an exact fertilizer. Instead of using 10-10-10, we might want to use a 20-04, something like that. So we're going to base it on a soil test. A soil analysis is the most accurate way to determine the tree's elemental needs. The test will result in information about usable nitrogen or available nutrients in the soil. It'll also provide you some extra information, such as soil pH. It'll tell you about some of the other essential elements, not just N, P, and K. It'll give you a quantity of organic matter in case you need to build up your soil, and it'll give you a CEC for your soil. How do you take these soil samples? You want to go back and sample over a large area. Get yourself a large plastic bin. Make sure that it's nice and clean and that you don't leave residues in it that might contribute to the soil test. So make sure it's nice and clean. You can use a soil probe, a hollow soil probe that you push down into the soil and you pull up, and it'll give you sort of this bar of soil. Take off the very top where the roots are, throw that out. There might be a little bit of organic matter at the top, throw that out, and then take the rest of that soil profile and dump it into your clean pan and go around and sample, I don't know, 25 places or so under a big tree all the way around, and just random areas. Don't get it all from just one spot. And then you're going to mix up all those samples, and then you're going to take about a cup of it and put it into your soil sample bag to send off to the university. That's going to give you an average, because even with under a tree, you might have had chemical washouts, you might have had concrete washout that occurred. Somebody might have been throwing their Clorox bottles out there for 60 years or something. Paint storage, paint dumps, chemical leaches. Someone might have dumped a bag of fertilizer, all kinds of stuff like that. Yes, ma'am. I see popping up again there.
Yep, it's me again. We just have a quick question. Do you need
Okay.
a prescription like medicine to be able to obtain that fertilizer?
No. So you can actually purchase fertilizers in their individual components. So you can just purchase the nitrogen, you can just purchase the phosphate, and you can just purchase the potash. And so you can custom blend it yourself to make this happen. Often, however, you'll get this prescription back and you'll be able to look at the prescription and go to a manufacturer, and the manufacturer might have something that's really close to that already. So you might not have to buy the individual components to get it exact. You just want to get into the ballpark. Remember, there's a wide range of acceptability. So just get close, so you can either make it yourself, or you can also have it made. There's several manufacturers around that'll make custom blends just for you or just for your area. If you find that your area all has similar soil or similar prescription requirement. So this prescription is filled by you, the arborist. Hopefully that makes some sense. We can also do a foliar analysis. This is through the leaves. So you take some leaf samples, send them in, and they'll be ground up, and they'll extract the compounds out of the leaves, and then they'll measure those compounds and let you know the same types of information that the soil test will give you. It can be pretty helpful in diagnosing certain micro deficiencies. Now, I'm on all these Facebook groups, and so I get these ads for stuff all the time. And one of the ones that's pretty popular is this little device. I'm sure you've gone to the doctor and they put this oxygen sensor over the end of your finger, or you might have a watch that does it for you, or something like that, that measures the amount of dissolved O2 in your blood. They have something similar for leaves, so you can clamp this thing over a leaf and it passes light through it, and it can give you some fairly accurate information. However, you need to have that same randomization that you had when we talked about pulling or extracting soil samples. By using these devices throughout the canopy, they realized that the top of the tree was different from the bottom of the tree, and the branch tips were different from the interior. So sample some of the interior leaves, some of the top leaves, some of the bottom leaves, and that's what you should send off. So if that little device has taught us anything, is that there is variability within the canopy, just like there's variability within the soil. So that brings us to the end of this chapter.
Oh, thank
And,
you.
yeah, so the guy asked, or someone asked if wind-blown salt could damage trees, and it certainly can. So,
Well, thank
um,
you.
so like after a hurricane or something like that, especially around the Gulf Coast where it can blow inland and hit trees that are not salt tolerant, such as our loblolly pines and things like that. Even on the Carolina coast, we've seen a lot of salt damage on those trees where you've had high tides and flooding that comes in with the hurricane. So the salt can accumulate in the soil and do damage that way also.
Thank you, Rob.
You bet. All right. So I guess we're ready to start. We will begin here with chapter 10. This is diagnosis and plant disorders. This is actually what I do for a living. I am a plant healthcare operator and business consulting company. We teach people how to develop plant healthcare programs for their companies. So feel free to ask questions as we go along, or again, you may email questions to me at any time. My email will show up at the end of this presentation. So plant diagnosis and plant disorders, we're going to talk about them very generically today, but keep in mind that this is an international class and you may see things in your area that are quite different from the rest of the world. So we're going to try to overgeneralize a lot of these topics. You can also use that same kind of mentality for the exam. So the exam is not specific to any one particular area of the United States. It's actually all temperate regions around the world. But to really be successful at being a diagnostician, you should really understand your plant material. And I strongly recommend that you develop what I refer to as a 10 by 10. So these are the 10 most common trees or plants that you or your company deals with. And you should figure out what their top 10 disorders are. So it's 10 by 10, top number of the top 10 species that you run into, and learn as much as you can about those top 10 species. And that's going to solve over 90% of the questions that your company has to deal with. And I have an Excel spreadsheet with a little demonstration on it. It's really designed around the Carolina coast, but if you'd like it, I can certainly send a copy of it to you. And there's some instructions on the front page of it that tell you how to develop it for yourself, for your specific area. If you happen to be in the Carolina coast, boom, it's almost done for you. But anywhere else in the country, you're going to have to sort of start over and do it yourself. And actually, the learning process comes from doing it yourself. Again, this is something that you're going to want to find a mentor to help you with. Getting out in the field and seeing these things will help tremendously. Also note that things like we have pictured in the background here, this giant fungus, that the names of these things change quite frequently now. They were the same for hundreds and hundreds of years, but now that we can do extensive genetic testing, we've discovered they weren't exactly what we thought they were. So be on the lookout that some of these things, the names of these things can actually change over time when you're looking in books or Google. So when you do Google things, make sure that you're using Google Scholar and you're not just using the regular Google. So Google Scholar are going to give you articles that have been peer reviewed and are usable by the arborist. Also, again, working with a mentor out in the field that can show you these things is invaluable. When you think about diagnoses, we want to know if it's a living entity or a non-living entity. So is it a living or non-living disorder? Diagnostic principles and approaches. We'll talk about how to do this over and over again. The relationship it has to that stress has to all of this. We'll talk about the difference between signs and symptoms of tree disorders. Again, biotic and abiotic, which is living and non-living. Physiological disorders and injuries and their treatments. We'll talk about some of the insects and diseases and their impacts in a fairly generic, broad strokes. So let's think about these. What is a living or biotic disorder? Living and biotics, these are caused by pathogens. There's a bunch of pathogens out there. There are fungi, bacteria, viruses, phytoplasms, and then we've got some other things like insects and nematodes and mites and animal damage. So there's all of these things can have an impact here. This is a virus, in case you didn't know what a virus looked like. They are typically infectious because they can spread from one plant to the next. Here in Central Texas, oak wilt is a big problem, and it can spread via the root system. So once a tree is infected by a nididulid beetle, that particular pathogen can travel through the root system to all the other oak trees that are connected, that have that interconnected root system. They do not travel through mycorrhizal associations, but they can travel through direct root grafting and spread. So that would make it infectious if it can go from one to another. Abiotics, these are the non-living environmental problems. They are non-infectious. Things like temperature extremes, mechanical injuries, chemical injuries, mineral deficiencies, drought, flood. All of these are abiotic disorders. They are non-infectious. So I'm going to give you some examples of an abiotic disorder. Here is a live oak tree not too far from where I live. It's got a fairly nice, healthy canopy. Let's take a look at it. You'll notice that there's a little bit of tip decline. We had a major freeze. So here it is to begin with. Notice that it goes all the way, leaves go all the way out to the tips. We have this major freeze, and immediately we have some canopy dieback in the background. You see another one, and then it goes to this. So this is an ash tree which was hypersensitive to temperature extremes. So again, this live oak went from this to this, but this tree is still alive. The one behind it, not so much. This is an ash tree across the street that absolutely could not withstand the temperature extreme. And when I say extreme, we had -5 degrees Fahrenheit here for a few hours, and we had -5-degree temperatures for over a 24-hour period. That is well outside of what these trees should be able to tolerate. Even the live oak should not be able to tolerate temperatures that cold, but there is some genetic variation. So you have some that die and some that don't. And here's an example of that. So this is that same tree. This is a year and a half later. And so the canopy has fully rebounded, and this tree has now since been removed. It just couldn't withstand, and they were the exact same species of tree, planted at the same time. So you can see that even though they were exactly the same, they weren't clones. They were raised from acorns, which makes them naturally occurring, and slightly different responses. In a general diagnosis, you could think about complexes, and these are combinations of things. So we've talked about abiotic and biotic. And so the two things combined make it a complex. You could also have two different types of biotics or two types of abiotics. As long as it's more than one contributing factor to the decline, we refer to that as a complex disorder. So we could have a combination. So it's a combination of these factors, biotic and abiotic. They can be secondary diseases, insects or diseases. They might have non-specific symptoms. So avoid concentrating on symptoms instead of the cause. Remember when we talked about chlorosis and we said, wow, this pretty, all these different things can cause chlorosis. So instead of, it's like, okay, well, I see it, so I know something else is going on. Let's try to figure out what the cause is. So 70 to 90% of all plant problems result from adverse cultural or environmental conditions. So our buddies, the landscape architects and homeowners, and I pick on the architects all the time, but keep in mind that importing a tree into an environment where it really shouldn't live is going to create a constant stress environment. That constant stress environment can certainly result in problems. Just like a smoker who smokes every day, might not be a big deal when you're a teenager, and still might not be a big deal when you're in your 20s, but you keep doing it into your 30s and you'll begin to notice changes in your body compared to those that don't smoke. Then your risk of lung cancer goes up tremendously over time. So smoking is a constant stressor. It might be a low grade stressor, but it's a constant stressor in your environment. So just like having the wrong plant in the wrong place. Now, I can't stress this part enough. Don't guess at what the problem is. If you don't know, if you can't figure it out, ask for help. Develop a network of professionals that you can go to and say, hey, what is this disorder? What am I looking at here? Can you help me? Take lots of pictures. I do a lot of virtual work, and people from all over the country will send me pictures. My biggest complaint about pictures is the resolution. So if you're sending pictures to someone in your support network, make sure that you're setting your camera on fairly high resolution, like 1 or 2 meg and not 300 megabytes. You want something sizable. So and make sure that it's clear. Wipe your lens down before you send pictures. 80% of the pictures I get are blurry and low resolution because they didn't wipe the lens on the camera. They just took a picture. Obviously, also, people don't know exactly what it is that I might need to see to help with the diagnosis. So when you're sending pictures to people, make sure and take pictures of the actual problem up close. Take pictures of the overall tree structure. Take pictures of the base of the tree, then stand really far away so that you can take a picture and, because up close, I might not be able to tell that it's a commercial environment or if it's a residential environment or if it's in the woods. It's take pictures far enough away where I can gather some or someone can gather that type of information. So make them clear, make them high resolution, and give them a diversity of pictures, and be prepared to take more pictures. Once the person helping you sort of gets a clue of what's going on, they might ask for something specific. So be prepared for that. And again, don't be, you'd rather be right than wrong, no matter what. Your clients will not see it as a weakness even if you say, I don't really know what's going on here. I have a network of experts that are going to help me out, and I'll get back to you with an answer. Sometimes you might even have to send off materials for testing. So the expert might be the university testing lab. You want to be very systematic. And I can't stress this enough. Don't jump to conclusions. Don't say, oh, I've seen this 3 or 4 times already. I know exactly what this is. Try to avoid doing that, because if you do it, you might overlook another cause. Remember, we've already talked about the number of things that can cause chlorosis. So do it the same way every time you do it. I like to start at a distance and I spiral around the tree, sort of in a reverse Fibonacci kind of curl, like you're going towards the inside of a snail. If you're on the inside of a snail shell, you're getting tighter and tighter each lap you make. So when you start off far to the outside, you're looking up at the canopy, you're trying to collect as much information as you can. You're getting a little closer, you're looking up the ground, and then you're getting a little closer and you look at the structure up in the tree, looking for hazards, broken branches, insect damage, hypoxylin damage. There's a number of things. So collect all the information that you can as you're spiraling in, and eventually you're going to be looking right at the base of the tree. You might be looking at leaves up close as you get really tight. So begin with accurately identifying the plant or the tree. If you don't know what you're looking at, then you don't know what it's supposed to look like. I get calls every year about the bald cypress. In the fall, someone inevitably calls and says, my pine tree's losing all of its needles, it's dying. And I'll quiz them a little bit, and I might find out that it's a bald cypress. And it's like, well, ma'am, that's exactly what it's supposed to be doing this time of year. So that's a normal activity. It's not abnormal, but I wouldn't know that if I didn't know the species. So accurately identify the plant. Know the difference between normal and abnormal. Again, this is where that 10 by 10 can start helping you out. When you're recording, say it's white oak or Leland cypress. If you've seen tons and tons of Leland cypresses, you're writing down Leland cypress, and then you might have all the disorders that Leland cypress can have. They can have, Botsypheria, they can have Cercospora, they can have Ceridium blight or Ceridium canker. So there's all these things that they can have. And when you're putting together your 10 by 10, you're saying, okay, here's a link to my Leland cypress site that has all these problems on it. So know what it, and it'll have things, record in the plant part. What's the right spacing for this plant? What's the right pruning frequency for this plant? What's the right soil environment for this plant? What's the right amount of fertilizer for this plant? And you can find all that stuff. You have to do some research. That's part of the learning process to help you do this on your own. I've been doing this for 33 years, and I learn stuff every single week. I learn something new. I'll see it and I'm like, man, what is that? And then I'll start doing my research, and then I'll start sending pictures and uh, things to my friend, to my network of other arborists, and say, what do you think this is? So start with knowing your plant, knowing what it should be, and then look for a pattern of abnormality. Is it uniform throughout the whole canopy, or is it just the tips, or it might just be one branch? So this pattern of abnormality is a big issue. So how is it exhibiting the disorder? Here we have, again, this oak wilt in red oaks can travel quite quickly, but it typically starts off with one leader turning a different color. So you'll have one yellow leader and the rest of the tree look fine. You come back in a week and it's the whole tree that looks yellow, and you come back the week after that and the whole tree's dead. So there's a pattern of that abnormality that might lead me to look a little closer into oak wilt. We as diagnosticians, we get typically one shot to answer a question. And you want to collect as much history as you can, but consider also that it's going to be painted through the lens of the person speaking, who is probably not an arborist. So you have a homeowner that might have lived there for 2 years and not really know the whole site history. They might tell you things like, well, it's always been like that. It's like, well, okay, well, always. How long have you lived here? 2 years. Oh, so it might have only been like this for 2 years. Well, yeah, that's right. So your interrogatory, your question and the answers need to be pretty thorough. Make sure that you're trying to find answers to specific things, like, has there been soil damage? Has there been construction? Did this used to be a parking lot? Do you use a chemical company to do turf applications? Do you do it yourself? Do you do weed control yourself? Do you do pest control yourself? Did you install an irrigation system? Have you redone your septic system? All these things might go into this site history. So collect as much information, write it down so that you're developing a history. Examine the foliage for color, size, and thickness. Leaf symptoms may be caused by problems elsewhere. We frequently use a product called Cambistat in the industry. It's a growth regulator, and it causes the leaves to be pretty small and pretty thick, but they're really healthy. But it might give the tree a weird look. So a homeowner that just purchased a house where Cambistat was applied a couple of years back are seeing these symptoms, thinking the tree is sick, but in reality, it's not. So, and there's a lot of genetic variability within foliage size and color. So if you're having giant leaves out in the open sun, well, that's kind of weird. If you're having these tiny little leaves in the in the shade, well, that's not normal either. So think about where and how the tree responds and how it may grow these. And we'll talk about that in a different section. But so you're examining the foliage. So these are things you can do from a distance. So you can identify the tree from a distance, you get the pattern of abnormality, you can collect your site history, you can look at the foliage and all that sort of stuff from a distance. Then as you approach the tree, you might start looking at things like bark and trunk and branches, looking for cankers, wood rot, borers, bark beetles, water sprouts, or you might see bore holes. You might see frass at the bottom of the tree. You might see a mushroom growing at the tree, but not really see the wood rot. You might see depressed areas on the trunk, but you really don't know if it's a real canker or if it's something else. So this is just, you're collecting information. Examine the roots and the root collar, dig down into the soil a little bit, pull out some of the fibrous roots, take your fingers and strip some of the outer coat covering over the roots and see if it's white or if it's brown or if it's black. These things will all tell you something. You can also smell the soil. Anaerobic environments like that have been supersaturated or soil compacted or fill dirt, things like that. If you poke through the fill dirt down into the original layer, you'll get this waft, this odor that'll tell you that that's an anaerobic soil environment. Aerobic means oxygen, so it's an oxygen process. Anaerobic means without oxygen. So that's sort of your spiral, and try to just keep your mind clear of jumping to a conclusion the whole time that you're doing this. So you're wrapping yourself into the tree, you're looking at all of these different aspects. Then once you've collected it all, then you can start coming up with what the problems might actually be. So an arborist must look for symptoms or effects of the causal agents that are apparent on the tree or how the tree responds to the disorder. So again, these are symptoms. Symptoms are things that can have multiple causes, such as chlorosis. It could be a micro deficiency. It could be insect feeding. It could be a number of things that cause chlorosis, a nitrogen deficiency, a magnesium deficiency, a zinc deficiency, a nickel, any of those can cause some chlorosis. You might have wilting, which would occur if there's salt in the soil, if there's not enough water available in the soil. It might just be normal wilting during the middle of the day, things like that. Look for leaf scorches. There's a number of things that cause scorches. Bacterial leaf scorch, BLS, can be caused by bacteria, but you can also have just plain leaf scorch from too much heat. We also, I told you about our drought this summer, so we also had almost 3.5 months of temperatures that were in the hundreds every day. And a few of our days actually hit 111 degrees, which is not normal. I mean, it's normal to be hot here, 100, 101, but 110 is getting out there. So all of those environmental conditions could lead to leaf scorch. If I have enough water loss, the tree might defend itself by defoliating itself, or insects might eat all the leaves off, or caterpillars might eat all the insects off, stuff like that. Branch dieback. So I could have dead branches from mechanical reasons, such as somebody left on the guying stakes too long and the tree grew and incorporated the guy wires, and from that point up it might die. That's another thing to add to your Leland cypress stuff. If you ever see the bottom half of the Leland cypress perfectly green and the top half dead, it's probably because somebody left the guy rope on there and the tree grew into it and choked itself, and it eventually died from that point up. But there are other things. There's root loss. There's a number of things. So these are all symptoms. So they can have lots of different causes. Compare that to symptoms. So symptoms are direct indications of the primary, secondary, or tertiary causal agent. So it's a direct indication of the causal agent. In the case of fungi, you're going to have conchs, mushrooms, the types of spores. So if you If you see this at the base of your tree, you know it's not the best thing. It's an indicator that it is a sign that it has a fungus. And this particular fungus is a delignifier, so it munches away at the strong lignin that makes the cell walls and stuff like that, and can lead to whole tree failure. So this is one to know. Insect frass. So frass is the byproduct of something chewing into the tree. So ambrosia beetles will bore into the tree, and as they bore in, they're ingesting the wood. It passes through their body and comes out the back end, and it looks like this little toothpick sticking out of the tree. And there might be hundreds of these little toothpicks sticking out of the tree, but it looks like it stuck in and then someone broke the tip off of it, so it'll come out and have a little crooked end to it. And that is a direct sign of insect damage to the inside. You might see emergence holes, and we have the emerald ash borer is a big deal, EAB. The exit hole makes a perfect D shape like this on the trunk. It's not quite this big. This is probably twice as big as the hole, but it's still a decent sized hole. And it's obvious that it has this D shape to it. And then sometimes when they are, this is an emergence hole. It's how they get out of. So the larvae have done their thing and they're turning into adults, and so they're going to come out of the tree. Sometimes as they come out of the tree, they can actually shed their skins right there in the hole. So sometimes you'll see a hole and it'll have just sort of an exoskeleton, and that would be the discarded skins. You see this often in maple borers. When they come out, they'll leave their old body there, and then their splits open and the adult flies away. So here are the common tree disorders. These you can have blights, and again, I'm not going to use specific names because there are different blights all around the world. So just generically understand that there's blights, cankers, chlorosis, decay, dieback, galls, gummosis, leaf blotch. So there's blotches and there's spots, and so there's fungal things, and then there's bacterial causes. So each have their own little leaf pattern. You could have leaf spot, necrosis. Necrosis just means dead tissue. Powdery mildew. This is something that grows on the outside of the plant, but if the leaf can't get enough sunlight, then the leaf dies. You can have rusts. These are usually alternating problems, which means they need more than one host to pull it off. Scorch is when the leaf gets crispy. And again, there's lots of causes for that. There's there's stunting, so the leaf might partially emerge and then get all contorted and funky looking. This can often happen from pesticide use. Herbicides especially can cause deformed leaves and deformed twig tissue. Vascular discoloration. Around here again, we have that oak wilt. Oak wilt makes a very distinctive coloration on the leaf of a live oak, but it can impact all oaks, but the live oak's the only one that shows this really funky vascular discoloration. We can have wilts. You can also have witch's broom. This is a thick tuft of plant material that grows off of the trunk or off of a branch, so it's very distinctive looking. So look through your manual, and hopefully you'll see some examples of all these things. Look them up. Go to, again, Google Scholar, type in powdery mildew, click on pictures, and you'll see some examples. On necrosis, trust me, you want to have a modifier in here like leaf necrosis or vascular necrosis of trees. Otherwise, you could wind up with some pretty gruesome pictures on Google Scholar. So stress is another thing to consider. When we're doing this wraparound investigation of the tree, not only are we looking for signs and symptoms, but we're also looking for possible causes. Tree stress, again, comes in the acute format and the chronic format. Acute means that it's quite sudden, it's immediate, like the or the freeze damage that I showed you in those slides. That is an acute stressor. I can point to a single event and say, this is the day that it happened. So it can be very specific about it. Or this is the day that the herbicide was applied and it resulted in, death of the canopy or contorted leaves, things like that. So those are acute stressors. The other ones are chronic stressors, and they can occur over a very long period of time. Things like mineral deficiencies, the incorrect light amount, long-term weather patterns, improper pH, wrong tree in the wrong spot. We see this a lot in street trees. Street trees have a fairly limited soil root space. They may be planted in downtown areas with very tall buildings, and so we create these urban valleys. So the sun doesn't come over this building until 10, and then it sets at this building at 1. So it just gets a few hours of sunlight every day. So it's not enough to reach its 100% potential. So it's a chronic stress that it doesn't have enough sunlight. In these small planters, the soil either was no good to begin with, or it was pretty good, but no one came back to maintain the nutrients in the soil. And so over time, you can have this slow degradation of minerals from the soil as the tree uses them up. We can also have long-term weather patterns. Around here we had those ash trees that were planted back in the 1970s. We never had weather that was cold enough to damage them, and then all of a sudden, out of nowhere, we have weather that's cold enough to kill all these ash trees. So we have in general, our weather's becoming more extreme, both in heat and in cold. And so as this happens, and we're going to see more and more of this, that trees that were at one time able to live in a specific zone, now you might have to rethink the zones a little bit. You might not be in the same zone you were 25 years ago as you are today. You could also have improper soil pH. So as we showed earlier, if it's too acidic or too basic, you can tie up some of those compounds. Street trees, again, this happens all the time, where the pH will change a little bit over time and make things less available. And then the site selection and adaptability, you just didn't have the right plant that would adapt to that environment. So it's a constant stressor. Now let's talk about a few of the abiotic disorders. We have soil and site problems, issues with the root flare, such as string trimmer damage, installation damage, like somebody put their foot on the side of the trunk, leaned back and hauled on the tree, and wherever their foot was created some compression damage, which might not show up for 5 or 6 years after installation. You can have sun scald occur down at the root flares. Physical and mechanical injuries, physiological disorders develop over a long period of time. Temperature extremes, you can have these frost cracks and sun scald. Both of these, obviously sun scald comes from the superheating of one side of the tree, and frost cracks occur when high levels of moisture in the tree freeze and expand and destroy the vascular tissue. You can also have hail damage. So hail can knock all the leaves off the tree, or hail can do so much leaf damage that the tree itself decides that it's too much trouble to hold on to all these damaged leaves, and it just wants to put on a new set of healthy leaves. So it might instruct the leaves to fall off on their own. You might also have some competition or allelopathy. So this allelopathic behavior, the typical example is the walnut. The walnut is in the juglans family, and it's known because in the root system it produces this chemical called juglans, and nothing wants to grow in there except for a walnut. So when I was a little kid and I'd walk through the forest, I would see these walnut trees in the middle of the forest, and there'd be nothing growing underneath the canopy. So wherever the critical root zone was, the concentration of juglans was high enough to inhibit the growth of all other plant material. However, today you walk through the forest and you will find privet growing under under all these walnuts, because apparently privet's unaffected by the juglans. So, but that is an example of allelopathic behavior. Another example of allopathy is that grass roots can actually produce a chemical in the soil that inhibits the growth of tree roots. So you would normally find kind of barely any, if any, overlap of grass roots and tree roots with each other because of those chemicals in the soil. You can also have pollution damage. So back in the 80s, Atlanta used to have tons and tons of white pines. As the ozone levels increased in the city of Atlanta, the white pine is fairly sensitive to ozone damage, and so we started having this decline of the white pines. I was on a radio show in the mid 90s, and someone was asking about the decline of all these trees, and I told them, well, it's mysterious pine decline, and I was joking, but now you can actually find that terminology around MPD, mysterious pine decline, but it was really something that I just made up to explain the pollution damage. So be careful of what you say and what's recorded out there, because it might come back to you at some point. You can also have chemical injury. This is considered abiotic, that can be systemic, such as a herbicide, and you can lead to phytotoxicity. Systemic means that it's translocated throughout the plant. I'm assuming that you guys realize that all these things that are underlined here, these are things that could be on the exam, so make sure you know how to define them. There's also water availability. Again, it's just not getting enough water, or you could have girdling roots. Trees in the nurseries, if they're left in the pots for too long, and Kay might have already talked about this, but if they're left in the pots for too long, they can begin to circle. And so as the tree puts on secondary growth, as it gets larger and larger in development, and the roots get larger and larger in development as they grow, eventually they'll hit each other, and it will begin to deform or choke the main stem of the tree. So there's this root that's now choking the main tree, sort of like the example I explained with the Leland cypress that had the cable left in it that killed it from that point upwards. Some insect damage and some other pests. So insects, so the leaves can be damaged by the feeding or egg laying activity. Chewing, boring, piercing, and sucking. These are all different mouth parts of an insect. So you have chewing mandibles, you might have boring mandibles, you might have piercing pieces. So think about a mosquito can pierce your skin and suck your blood. So that's kind of what aphids do. That's what scale does. There's a number of things that are piercing, sucking. Boring or chewing might be caterpillars. Boring might be things like the ambrosia beetle. You can also have skeletonizers out there. These are little animals that eat everything except for the veins. So you have I'm sure you've seen some of the artwork where they take these leaves and they dip them in gold, and it looks pretty cool because all you see is the veination of the leaf because everything else is missing. That's caused by a skeletonizing insect. You can have honeydew sooty mold as a result of things feeding on trees. So just as an easy example, if you think about aphids are constantly feeding on photosynthate. If you remember what photosynthate is, it's a sugar, it's a carbohydrate, so it's constantly consuming these sugars, and it's a tiny little thing, but it can suck a lot of out. And so as it passes through, most of it is not digested, most of it's not used for energy, so it's taking it and it's excreting it out the back end, and it might constantly be dripping from the tree, and you have this sticky mess underneath the tree, all those sugars excreted by the insect. That is what we call honeydew. Now, on the honeydew, because if you think about it, it's rich in carbohydrates. It might be falling into the shade because it's under the canopy of the tree or the plant. And so it can begin to grow mold and turn black. and that is sooty mold. So sooty mold grows on top of the honeydew. Now we can also have vectors. So these are insects that can bring in a disease. So the insect itself is not the main culprit, such as the knitted doodled beetle here is a sap drinking insect. So whenever there's a fresh branch cut or there's a crack in the tree that exposes the vascular tissue, the knitted doodled beetle can go and drink that sap. If the knitted doodled beetle can be a carrier for oak wilt. So if it's carrying oak wilt and it goes and it drinks the sap out of a damaged oak tree, it can inoculate that oak tree with oak wilt. That makes the knitted doodled beetle the vector. Nematodes, these things are microscopic worms. They sort of look like worms, but they're super, super small. You have to see them under either an observation scope or a microscope like I have in the background back there. Mites are a type of spider, so it's an arachnid. It actually has a certain number of legs at one stage in its life and another set of legs at a different stage. So that's what makes it kind of weird. That's why we call it a mite instead of a spider, though both mites and spiders are in the arachnids categories. Other animals that feed on the bark tissue and phloem tissue could be woodpeckers, sapsuckers, deer, rabbits, moles, voles, a number of things. Here, squirrels are a huge issue on pecan trees. They like to go and feed on the very tips of the trees where they can get moisture out of it and drink that moisture. But as a result, you get these the last 2 or 3 feet of every branch will die off or just scattered throughout the canopy. Woodpeckers can carry a complex virus into sweet gums. So you might have seen sweet gums with the very top of the tree that's dead. So the sapsuckers will go and hammer in, fly away. The hole weeps a little bit and they'll come back and drink that sap. But at the same time, they can carry a disease from one sweet gum to the next while they do this. So sapsuckers are a woodpecker. They're a category of woodpecker. If you ever see all those holes perfectly lined up on the trunk of a tree, those are sapsuckers. Deer like to rub their antlers on the trunks. Rabbits like to munch on the small fibrous root tissue, stuff like that. Tree have to, so we talk about this sort of disease triangle business. Trees must be susceptible to the pathogen must be present, and the environment must be suitable for disease development. This is the disease triangle. So we have each side of the triangle that has to be present. Again, so the species has to be susceptible to the pathogen, and the environmental condition means it has to be the right temperature, the right time of year. All of these things have to coincide. So you might have species as one leg, pathogen is one leg, and environmental is your other side of your triangle. So again, you have to have all these things in place in order for the disease to actually manifest. Going back to oak wilt at 90 degrees is dead. It doesn't do anything. So just because I have an oak tree and the pathogen might be there, the temperature is too high for inoculation. So inoculation won't happen when it's in the 90s. So I'm not going to get it. However, if I have a maple tree and I have the knitted doodled beetle carrying oak wilt, and the environmental conditions are such that it's the oak wilt's alive, since the species not there, I won't get inoculation. So you can kind of see where I'm going. You have to have all 3 of these things in place for that to happen. Most pathogens are host specific. So meaning that Dutch elm disease is just going to impact things in the elm family. Oak wilt pretty much just impacts things in the oak family, though you can also find something similar to oak wilt in the wine industry that attacks the grapevines. Also, note the part of the tree that's affected. This can be an indication of the severity of the disease. In other words, is it just in the leaves? If it's just leaf spot, plain old regular run-of-the-mill leaf spot, would you really need to do anything about it? Probably not, because it's going to drop leaves and grow new leaves the following year. And the leaves might even persist for the whole season. So they're still manufacturing plenty of photosynthate. So not to worry. Or is it vascular in nature? Is it bacterial leaf scorch that's in there plugging vascular tissue, causing all the leaves to fall off or die? Is it one little section of the canopy? Is it just the tips? Is it a whole branch at a time? So vascular things are pretty bad, like oak wilt. It can kill the whole tree in fairly short order. Just keep in mind that there are things that are just foliar diseases. There are just shoot and twig problems. You've got twig borers that might just chew off the last pencil size twig at the end of every branch, and you see raining down all of these, especially hickories and things like that, and oaks. You might see on the ground all these little branch tips, and you're thinking, man, what disease is going on here? And it might not actually be a disease. It might be an insect that's a twig girdler. So you'd look at the end of the twig and it looks like a sharpened pencil. That's a twig girdler. You might also have insects that are laying eggs out towards the branch tip. So they have an ovipositor or an egg laying structure to them that can saw a slit into the bark and put its eggs under the bark. Sometimes that can cause the outer 6, 7, 8 inches of the twig to die. Locusts can do that. Dogwood borers can do that. There's the last few inches of the magnolias that can get the tip borer, the magnolia tip borer that gets inside of the black twig borer can get inside of the twig and kill that last little bit. So knowing where the disease is and where to look for the signs and symptoms. Vascular wilt diseases, again, are just horrendous. Root diseases are very difficult to control also. Most root diseases are fungal in nature, but you can also have nematodes that eat the roots or herbivores that are eating roots. But if it's an armadillo that's out there that's munching around, digging up roots and tearing the plant up, it's probably not going to do enough damage to kill off a tree. But if it's nematodes in a boxwood, then it can pretty much kill the boxwood pretty quickly. So knowing what the disease is, knowing how it manifests, knowing the species. Notice I had to put a species to give you an example on each one of those. Some things like, remember I talked about rust. These are alternating hosts. So you might see this in your exam, this alternate host, meaning that it has to have more than one host to pull off the disorder. The most common one is cedar apple, meaning you need a cedar tree and an apple tree in order to get this recurring rust. So one year it will be on the apple tree and it kind of makes the leaves look really cool. They turn all these odd colors, makes it look like a calico cat or a combination of fall and spring all at one time. Really cool looking colors. And then on the cedar tree, when the pathogen inhabits the cedar tree, it looks like this stringy thing from outer space. And it'll just be one little clump inside of the cedar plant somewhere, or the juniper, that you might not even notice unless you were looking for them. If you have cedar apple rust, one of the things might be to cut down all your cedar trees, so you take away one of the hosts, and then it'll die out in the apple population. Or if you like cedar trees for some reason and don't like apple trees, you can take out the apple and just leave the cedars. So that breaks it breaks the cycle. Yeah, so there's a number of rusts out there, and they all have kind of these alternating hosts. Fungi are responsible for the majority of all plant diseases. Bacteria and viruses. So bacteria they have a nucleus to them, and so they can replicate that way. Viruses really don't have a nucleus. So, but they can, just like you get a bacterial disease, you can take an antibiotic for an infection. You get COVID, which is a virus, you really can't take anything like, there's not any real true antiviral medications. You can just teach your body how to respond to it before it gets the problem. So that's why we get vaccines and things like that. We might use things to improve our metabolism so that the viruses are less impactful, but you're really not having a direct impact on that virus. There's not just one thing you can take to make that better. Management of plant diseases is an exercise in prevention. So you're planting the right tree in the right place, giving it the right environmental conditions. You're maintaining those conditions so that the tree's always in good health. And so that's, if it does have a fungus or there's fungus in the area, you can apply fungicides preventatively and they work very good. They do not work very well, as that you cannot cure a fungal problem. You can just kind of manage it. Global commerce and travel have increased the importation of non-native species of insects, diseases, and invasive plants. The emerald ash borer is not native here. It came in through a port, I think maybe in Chicago, and it radiated outward. The Asian longhorn beetle, there's lots of things that have come in and have just taken over the country. So how can you get assistance? I said, you could develop your own network. You can also send things off to the laboratory, to the university. So at the universities, every state has an extension office. So these local cooperative extensions in Georgia, it's run through UGA. There's also testing available at the federal level through the USDA. Keep in mind, samples should be taken from representative portions of the plant. So if you have twig dieback, take a little section of the dead twig, some of the dead leaves, some of the live tissue up there, transitional area where you think that the pathogen might be active, take samples from all these areas. Package them up accordingly. Here, when we send in oak wilt samples, we're taking the sample, we're putting the leaves separate from the woody material, putting them in baggies, putting these baggies inside of coolers, and then putting a chunk of dry ice in with it, taping up the cooler and dropping it off at the university. That way they are getting a fresh sample with the pathogen still alive in it by the time they get it. When you're dropping it off, most extension services have like a table set up and all these sheets, and what do you think it is? What is the sample? Where did it come from? What species is it? What were the environmental conditions? What do you think it is? Stuff like that. Help give them some direction. When you're doing chemical damage testing, this can be really hard. You can't just send in and say, I think that it's chemical damage. Say something like, well, it's herbicide damage, or it might be gasoline or diesel fuel of toluene from cleaning out parking garages or construction site cleanup material. All these things can kill trees. So they're pretty hard to pin down unless you might know what have happened. Say, well, it was a construction site. So then they might look at soil pH, things like that. So give them as much information as you can. Rarely is the real problem a simple matter of isolating a fungus or identifying the pest. So just because I know that there's some fungus at play, the real problem is maybe it has too much irrigation. Maybe it's the wrong tree in the wrong spot, something along that. It's usually more complicated than just this one issue. All right, so that brings us to the end of this section. Again, if you have questions or if you want a copy of that 10 by 10 for your own file, let me know. I'll email it to you. Put something in the subject line that says something about our class so that it doesn't go to junk mail.